This question, exercise 1A7B, I think had probably the widest variety of answers submitted or possible solutions submitted. And I wanted to point out a couple of things that are really important about a question, this question and others like it. And I think that its distinguishing feature here is that they give you data. I know it's only 3 points, but as soon as you have more than 2, you have the possibility of taking that information and creating some sort of a graph. Now, if we look at the wording of this question, which, by the way, is, in my opinion, a little bit messed up in the data that they've given you, but anyway, they say that the following data have been obtained for oxygen at 273.15 Kelvin. Calculate the best value of the gas constant R from this data and the best value of the molar mass of oxygen. Okay, I want to just focus on the value of R for the moment. And their wording of the best value. So what a lot of you did was to apply PV and RT because we have temperature and we have pressure and volume and we know that it's oxygen. And you calculated a value for R just by rearranging PV equals nRT. We don't have N, but we have the molar volume, so the only unknown was, not even, but we could calculate for R. Here it's an unknown. And then you did the same thing for this and the same thing for this, and because we know what R is supposed to be, and its real value, then many of you said, well, I'm looking at the 3 values of R that I calculate for each of these data points, and I'll choose the one that's closest to what I recognize as the real value of R. And so you chose that as your best estimate. But that's not what that means when the question is using phrasing like best estimate. Think of best fit. So what you need to do is to graph the information and derive your unknown from something from the graph. So we're looking for a value for R, and that R is the gas constant. So it should come from some constant part of a graph. And so if I can graph this in the form of a straight line, I would expect an R value to come out of either the slope or the intercept. So let's just play with PV and RT for a second. All right, so if I have PV is equal to nRT, and so PVM is equal to RT, I can see that P is equal to RT1 over VM, like so. And so I could probably make a graph that looks like this and put pressure on the Y and 1 over molar volume. I would expect a line because these are related through a constant. And I would expect that the slope would be equal to RT, and T is known, so I could get my value of R from the slope. That's one way we could have done this. Another way that you could do is, and this is what the book suggests in somewhere in the chapter, so go back to PVM is equal to RT, and they isolate for R, so R is equal to PVM over T. So PVM over T, and T is the same for everything. So the idea here is you could graph, sorry, I'm stalling because I'm looking at temperature. Yeah, I need temperature. So R is supposed to constantly equal this PVM over T. Okay. And so I could take, for every pressure, I could plot PVM over T. And they're going to be really close to each other, right? In fact, it should just be a scattering of 3 points that are really close to each other. And yeah, it's going to be almost a straight line. So just pull the data down here. Yeah, they're going to be quite close. So if for every pressure that I collected a data point, my PVM over T should be the same value. But it's a real gas, oxygen, and it behaves most ideally in the lowest pressure range, so as P goes to 0. So see, since it's a limiting law, in the limit of pressure going to 0, I would have PVM over T equaling my best value for, or best estimate for R. So in other words, put the 3 points on here, best fit them to a line, extrapolate the line back to get your y-intercept at x is 0 or p is 0, to get the limit, the limiting value of PVM over T, and that should be your best value of R, because it's where the pressure is going to 0. Right? So that's how we deal with that. Now, having that value, then you can work it in to the equation PVM equals RT, and or PV equals nRT. Open up N as a mass over molar mass, and then get your value for the best value of the molar mass. So that's how I would suggest to do that one. So again, what you want to avoid, okay, next time, next time I won't expect you folks to do each as a calculation and choose the best, but rather take this experimental data, because that's what it is, plot it, and think about it being a limiting law, and thinking that my best estimate is where P is equal to 0. And so this is the best way to do it. I haven't done these side by side to see which actually gives me the better estimate of R. This one would, as I said, not here, sorry, up here. This one would give me the slope. R would be in the slope. And so R would be equal to the slope divided by temperature. Excuse me. And down here it would be the intercept. But again, I'm taking data, I'm fitting it to a straight line, I'm looking for the best estimate of a constant, and the two things that are constant on a line are the slope and the intercept. So I'm making use of one of those ideas here. R is coming out of the slope, or R is coming out of the intercept. So think about those types of questions in that manner when we have to answer them. Now, getting back to the data that was given. See, the data that was given, well, I did write it back out. Pressure and molar volume. And I was curious, I looked at some old versions of the book where they had not the same question, but the same style of question. And they gave, it reflected more, the data that they gave reflected more the experiment that's actually done. And so the pressures were there, they were listed, but not the molar volume. What was listed was the density. And when you think about it, that's the kind of experiment that would be done. You change the pressure, you measure the density, and you say pressure is a function of density, and density is mass over volume, and we know that we can work in a density in the PV-nRT equation. In fact, molar volume is molar mass divided by density. That's a really important relationship you'll want to know for the midterm. Again, molar volume is the molar mass divided by the density. Think about it. I've got grams per mole divided by grams per liter. So the grams go out. I have per mole over per liter, which is liters per mole. And so if you were to see this question again, you would probably see it as here are the pressures and here are the densities. And what you would want to do for yourself is convert those molar volumes, or pardon me, convert the densities to molar volumes, and you would know the molar mass because oxygen is O2, so when you have a periodic table. So you would have the information to convert the density to the molar volume. I think I just said molar mass earlier, but I meant molar volume. So again, molar volume is molar mass divided by density. Okay, so the couple of concepts here are really, really key ideas in this course. What to do with data and how to treat it in a graph and what to get out of that graph in a way that makes sense. For example, extrapolating back to zero makes sense because this is a limiting law where the pressure goes to zero. It works best at lowest pressure. Okay, so that's enough about that.